second lecture class.
Yeah, thank you. Okay, yeah, so I'm going to continue with my second lecture. I'm just going to get back to that. So let's briefly recall the outline. So yesterday we heard about quantum sensing, just in a general introduction. Today I'm about to tell you about quantum sensing, but now getting experimental. So we're going to take the one system that we use in our lab, and we send it in Diamond. I'm first going to show you some of the basics and then some applications. And then the third one for Friday is a particular application that we pursue with MV centers, trying to image molecules with them. But it actually contains a lot of quantum sensing, also what we've heard today. So this is a very nice combination then of really an applied goal, but using a lot of the tricks that we learned. So before I get to number 2, I actually want to get back to number 1, because I left out one chapter which was picked up by Murray yesterday, and also some of you were asking about it. So let me see whether I can enter my computer. Okay, so we've heard a lot about this right now. Heck, how can we get the best or most information out of our measurement? And the formula that we used yesterday, both me and Murray Holland, was that we just looked at, we counted 0 outcomes, 1 outcomes, and we derived some change in the probability that we wanted to measure and divided it by a uncertainty. So here, not using any Bayesian analysis, not using any picture information, our very basic picture. And we arrived in the end, we plugged in some numbers here for a Ramsey measurement, and then we had the projection noise here, this C factor that I'm not going to comment on, but that many of you had some issues with, that just quantifies how good is our readout. And we arrived with this final formula. And what I want to get back to is this square root of n here. So we saw our SNR is given by make the measurement long and have a good coupling. Then we have the quantity that I want to measure the delta V here. Some readout efficiency, which is 1 or less than 1. And we want to repeat the measurement as many times as possible. So we see if we repeat the measurement n times, we get a square root of n advantage. And this is with any sensor. So with any measurement, if you repeat it for basic statistics, you're just going to gain a factor of square root of n. So the question then I wanted to pose, but I skipped over, is if you now have not only 1 qubit, but many of them, n of them, how much better can they be? And the immediate answer, they're going to be square root of n better. But I want to now show you one more example. We saw one yesterday in Murray Holland, that you can get better than square root of n better, but up to m times better by using m qubits. And I'm going to show you now just one more example, which is, to me, it's an intuitive example coming from spin physics, where you can get beyond that square root of n limit. Okay, so let's go back to the square root of m. Let's say we have 1 qubit, and we see the noise that we get from that measurement is, well, 1 over then square root of 4n in the denominator, which is just a standard deviation of the binomial distribution. So if you repeat the number of the experiment n times, we get the square root of n advantage. Now we can add a second qubit, or third, fourth, and so on, n qubits. And what you then get is just, you parallelize your operation, so your noise is going to improve, because now for each measurement you get m measurements, so you just trade, either you do n measurements in a series, or you do m measurements in parallel and n in series. So you get just this product here of an advantage. So this is just, if you have m sensors, your square root of n better. Okay, so now the question is, can we do better than that? And of course, the answer is yes, we can. Otherwise, I wouldn't show the slide here. And the idea is now to start coupling these qubits and exploiting the entangled states or higher coherent states between the qubits. And I'm just going to show it for 2 qubits, but it very naturally extends to n qubits. So let's assume you have 2 qubits. Let's make them identical qubits with an energy gap and a small coupling. And let's assume the coupling is much smaller than the energy gap here. So you can put this in as a coupling string J, which can again be a frequency. So if you now couple the qubits, you can write 2 qubit states, and you're going to have 4 states. You're going to have a 1-1 state, let's say both spins pointing up, then both spins pointing down, and then the mid one will be 1 up and 1 down, or the other way around. And the energy gap here is roughly J, but I assume it's small, so they're almost degenerate here. But now if you look at the energy difference between the top and the bottom one, both spins up, both spins down, you have a double energy gap. So if I now start building up my change in probability, we saw it's proportional to time and our frequency. If I have 2 qubits, the frequency from here to here was nu, but from the top one to the bottom one is now doubled. So I have a frequency difference of 2 nu. So the change in probability I'm going to build up in the same time is twice the probability change I had for 1 qubit. And if I had n qubits, and I'm able to get some superposition between 1-1 or then high state with only ones and only zeros, I can get up to a factor of n. So within the same amount of time, I get n times more build-up of this delta p. So you could expect our signal advantage is already going up as square past n. So how we do this? And the basic scheme is actually very similar to before. How can we produce this state? And it's again our very basic scheme. We can try to initialize our spins. Let's say we can initialize all of them in the 0 state. And then we have to bring them in our initial sensing state. So one very basic example with the Ramsey experiment, we apply a pi half pulse, and the pi half pulse creates a superposition, and then we start our sensing time t. In this case, we have to work a little bit harder. We have to find a way to entangle and to create this maximally entangled state here. But still very often for spins it's possible to do it. In this case, we can make still a coherent state. We can evolve for a very specific period of time, which is given by the coupling. And for the spins, we can create this maximally entangled state. Here our sensing time starts. We build up our phase shift, nu time 2 times nu times t. And then when we're done, we have to go back to our readout basis, so we kind of disentangle and make a readout. So at this point here, we go from qubit B, all the zeros. We have here the maximum entangled state with the sensing and go back to our readout basis. Okay, so now we can look at how this scales with the number of qubits. And let's go back to our initial one where we have n qubits, but they're all operated in parallel. We have no entanglement, and we saw that our uncertainty scale was improved by square root of m, but our signal is still the same. So the SNR in this case scales with the square root of the number of qubits. Now let's go to our entangled state. Now our readout is now only from one state. We operate the whole thing as one center, so we don't get this square root of m advantage here. But now, so we have the same uncertainty as before, but now we build up n times our probability difference. Our signal goes up by a factor of n, because we are now accumulating this phase difference n times faster. So if you combine the two, the SNR now goes proportional to n. And so this is now where we can advance from this just statistical limit by using maximal entanglement to go to a case where we scale with the square root with the total with the number of qubits n. So this is one example where you can, by using entanglement, going to this state here, and the key graph is this one here. We exploit now the energy gap between top and bottom, which is n times bigger, to get an n times phase advantage. So this looks cool. We now can get many qubits. Let's make things better. There's a caveat in many experiments. This caveat is shown again in our starting formula here. So we get now this advantage of m in front of our phase factor, but we're still limited by how long we can make our measurement. So assuming we can make our measurement time as long as T2, as before, everything is the same. But it turns out that in most cases, if you have this very highly entangled state, decoherence is faster. So we start losing, if we now account for this decoherence factor, by having a T2 which is shorter for the maximum entangled state, and by this we lose it. And in many practical examples, it's now, we have to weigh, you gain a factor of m by entangling, but you lose by having a reduced T2. And it will very much depend on the experiment that you do, whether this reduction in T2 is dominating or whether you're really gaining the m. So very often, your advantage is somewhere between square root of n and m, but in some cases it may make things worse. So the bottom line is you can, in principle, go up to this from square root of n to this factor of n advantage here, so having a much faster scaling of the SNR, but in practice, this line here will very often be shifted up because your T2 is getting shorter. Okay, so this was why I didn't manage to put in yesterday, but picking up on Murray Holland's talk, I thought that would be a good opportunity to give you another example, having several qubits that are now, in this case, entangled, but there are many other Cs that you can do. Sounds good? Okay, so now let's move back to our topic. So let's go to experiments, let's go to ETH centers. Back to our title slide. So these are diamonds. Diamonds that we use in our experiment. And what we're going to look at now here is qubits formed by impurities in diamond. So this one diamond here is the diamond that we usually buy for our experiments. They're about 3 to 4 millimeters big. And they're grown by chemical vapor deposition. So this one is transparent, has no color. It's a very pure material. So this picture, by the way, was taken in my office. And I have a postdoc who's a good postdoc, but also enormously good photographer. So he has these ways to create these images that are unbelievable. I'm going to show you a few more later on. So the yellow ones here are yellow because they contain a lot of nitrogen. So this is the most common impurity in diamond. Most diamond that is grows quite fast because there is nitrogen there that helps, facilitates the growth, and therefore it's incorporated in many cases. And this one has quite a high density of nitrogen, 1 part per million or more. This is already quite high density. And if it's high enough, then you get this yellow color. The violet one here is the same as the yellow one, but it was bombarded by electrons. Electrons knock carbons out of place, so they form vacancies. And if you then anneal the diamond at 800 degrees, the vacancies can diffuse and attach to a nitrogen, and you get a double defect. So it's a nitrogen next to a missing carbon, a vacancy, and then it's called an NV center. And these NV centers, we see they absorb green, they emit in the red. And if you have a high density, you get this violet color. So we send one of those diamonds to a facility that can irradiate diamonds with a high energy electron beam. I think it's mostly for food processing to make them sterile, but they have some secondary beams that we're ready to exploit. Then you anneal them and you get this very high density color. In most cases we work with these diamonds here, and we make sure that we have these nitrogen defects only usually near the surface, because we want them to sense something which is outside of them. I'm going to tell you a little bit more about diamond just in a second. So here's an outline of today. I'm going to show you some basics of diamond-based quantum sensing. So first I'm going to just tell you something about diamond, the NV center, and show you some example experiments, which are experiments that go with the theory from yesterday. So how can you apply the protocols that we've seen to actually see some measurement? And then I prepared 2 applications. One is we're trying to use NV centers for in scanning probe instruments doing nanoscale analysis of magnetic fields. So our group is working on quantum sensing, but also nanotechnology. So we're trying to combine the two. And the second one is something we don't do in our lab, but it is a kind of a cool area where you can throw in all your ideas that you have. If you have a very small sensor and you can use it in biology, what could you do? And if I get time, I'll also show you some of the ideas that have been brought out there. The third application we're going to hear on Friday. Okay, so let's get back to the NV centers. We have this lineup of qubits. So the NV center is a solid state qubit. You can say there are two types of solid state qubits. The one which are defects in crystalline solids. Diamond is one. There's also silicon carbide. There is quartz, silicon dioxide. Many of those materials have crystal defects. Some of them are fluorescent, which we're going to use here, and some of them have spin. Many of them don't. And the NV center is kind of special because it combines many of these special properties all in one defect. The other type of solid-state qubits are usually quantum dots, so either colloidal quantum dots or gate-defined quantum dots, where the readout is very often electrical. So let's zoom in and just put down a few more details on NV centers. So NV centers give this coloring. It's a nitrogen and an adjacent vacant site. It has a spin 1. It has 6 electrons, and they're arranged in a way that 2 of them are unpaired. The spin 1 has some additional consequences that we'll see. So it has 3 spin levels, and it also has a splitting already at spin speed. It's chemically an Nd-, so it has a negative charge that's collected from the lattice. There's also Nd0 and presumably Nd+. One problem that we sometimes face with is that the NV center loses its electrons by excitation. If it's Nd0, it becomes useless. Okay, initialization and readout is all optical, so it's optical pumping and fluorescent intensity readout. So we use a fluorescent microscope, I think very similar to track lines. So what's exciting with it has quite long spin lifetimes, not the longest one, but quite long ones. So the T2 can be up to almost milliseconds, and the T1 is in the order of 1 to 10 milliseconds for these spins. And this is very long. Electron spins typically have a nanosecond spin lifetime. And it's a consequence that this NV center is in a very rigid lattice. So diamond is almost a vacuum around the NV center. And the carbon nuclei here have the carbon has no nuclear spin in most cases, so it's C12. 1% is C13, which has a magnetic spin 1/2 nuclei, and C12 has no magnetic nuclei. So this is very advantageous because very often nuclear spins, they cause this rapid decay. Silicon is another host material, which is very good for spin qubits because it also has mostly no nuclear spin. By 3-5 materials, they always have a nuclear spin, and that's T2 is much shorter.
Question, are these lifetimes for deep centers or within the bulk or near the surface?
Okay, so good question. Are these for deep NV centers or some near the surface? So there's a huge range. This is why we put the big range. So if you move NV centers close to the surface, these numbers tend to go down. But there are many other factors. If there's too much nitrogen, this number also goes down. If you remove C13, this number can go up. If you go to low temperature, this number usually stays, but not that number goes up. So I'm just putting here some typical range. Usually work with NV centers close to the surface, let's say 10 nanometers, and then usually that number tends to go down. But this is an ongoing research question, and is one of the pressing problems. Another exciting thing is that you can work with them at room temperature. So for many applications, this is actually very important. But if you build up a lab, it's also nice. You don't have to install any cryostat, which most people have to do. You don't have to work in vacuum. It's all anti-alien optical stuff. So the hurdle to enter that field is very low. Diamond is extremely stable. So people have found NV centers in nanocrystals down to 5 nanometers. And there are protocols. You will see that we can measure DC up to gigahertz using these redoxometry measured methods or just the Ramsey methods. There are more techniques that we want to see Friday. And it's mostly sensitive to magnetic field, but if I have time, I'll show you some examples where it also reacts to electric fields and temperature. And the main feature here is that you have a piezoelectric effect or a lattice expansion effect, and they have an effect on the spin energy. So why are many people interested in V-centers? The main thing is it's a defect or a spin qubit which has a lot of good properties, not the best ones, but it all combines it in one single object. And so far people haven't found another type of spin defect which combines 5 or 10 properties that you all want in one single defect. If you look for just one property, let's say spin lifetimes, you'll find better ones. But if you try to combine everything at once, good readout, and then a good spin lifetime, room temperature, in the end, it's usually better. Okay, many people asking about diamonds, so I'm just going to give you a short crash course about diamond, because it's usually quite exciting to see where it comes from. So diamond is not the most stable form of carbon. The most stable form is graphite, and it only forms in Earth under high pressure. Usually high temperature. Actually, the temperature plays no role. This is thermodynamics. The temperature helps you to convert to diamonds. If you have a low temperature, it just doesn't convert. You can actually prove that you have a diamond if you heat it up in air to about 600 degrees, and it will start burning. You know you have a diamond in your hand. It's another crystal or gemstone won't burn like sapphire. So they're not really forever if you heat them up. Otherwise, it's extremely chemically resistant. It's almost impossible to do something with edge away. So the ones we use are synthetic diamonds, and the first synthetic diamonds came in the 50s, and it was actually a big debate until people were able to make diamond. And they made it by a so-called high pressure, high temperature synthesis, so mimicking Earth. Go to very high pressure, raise the temperature until they convert. And the bulk of diamond is still made by these methods. So the main industry segment is coatings of tools to make it very wear resistant. In the 80s, a new method was found, which is chemical vapor deposition, which is even higher temperature, but it uses methane and hydrogen, and it's a chemical growth method. And by now, this is the method of choice, because it's the purest method. So all the diamonds that we use are usually these chemical vapor deposition diamonds. You can make them small, so one easy way is you just crush them, which is hard, but it can be done, and get into nanocrystals down to 50 nanometers, which then is interesting to biology as biomarkers. You can make them even smaller, and there is a fun way that was, I think, discovered in the Soviet Union, and it didn't make the Western world until the Cold War was over. And so what you do is you take TNT and other explosive, you put them all in a closed vessel and ignite it, and what does form? High temperature and high pressure. So you form these very monodisperse, so-called detonation nanodiamonds. And I think this won an alternative Nobel Prize once for the most inventive deposition of old ammunition. So you make the diamonds out of ammunition. The cool thing is they're all mostly monodispersed, but they're pretty dirty, so we don't really work with those. We work with either those here or these platings. These are actually the smallest ones that can host EV centers. You can go smaller, and you could say the smallest diamond is an adamantane, it's a diamond oil. But there is some debate there. Okay, so this is just where all your diamonds are coming from. The one you have on your rings usually are a natural diamond, because people don't want to surprise the better half by a ring which has a synthetic diamond. It has to be natural. But it was all the research we most to be synthetic. Okay, so let's go back to the NV center. Again, NV center, you see the structure here. So you have an energy level diagram, and it has two types of energy levels which are important. The first one is the electronic energy level. So this gives rise to the fluorescence. So you have here the band gap of diamonds, which is an insulator, and in this band gap you have embedded the energy levels of the NV center. And usually conduction and valence band play no role. So you're left with these molecular levels here. So sometimes the NV center is called a trapped ion. It has just the energy level of the molecule. So it has ground state, electronic, excited state, so the energy is about 600 amperes, 630. It has a third singlet state, which is very important for the optical pumping process and also for the spin selective readout, as you can see. Interesting for us is the ground state, which has 3 spin energy levels. So let me just briefly stay with the electronic levels. So what you can excite them, so usually you excite them with green light, photons go up there, and then there's a red emission. There is a red shift, because usually excite to photon sidebands, and then it falls down again to photon sidebands. So the absorption spectrum is the black curve here, and there is an emission spectrum in red. There is actually 0 photon light in the center here, which is, would be the correspond with 1.9 eVs. So how do we do the measurement? We usually excite with green light. We just take some cheap lasers, 532 nanometers, and then we have single photon counters that detect in the red. So this is how we can detect the fluorescence.
You mentioned that these operate at room temperature, so you go back to the spin in another diagram, show the lattice vibrational vibrations giving the vibrational sidebands and others.
Yeah, so the question is, do the lattice vibrations give you sidebands? The answer is yes, they give you strong sidebands. The answer is actually here. So if you have no lattice vibrations, no sidebands, then, this is the line that you would expect. So all the emission you see at lower wavelength, or the absorption at higher wavelength, absorption at lower wavelength, comes from sidebands which are not indicated here because vibronic sidebands that extend up. So if you excite with a photon, you go usually to the higher vibronic sidebands, and then within picoseconds you fall down to the energy level. Then this decay here is in the order of 10 nanoseconds. So if you excite, you go up here very rapidly, you end up in the excited state, you wait for a long time. Mostly you decay on this path. Sometimes you take the detour here. And this is, you can see it in this emission spectrum. This changes if you cool down. It doesn't disappear, it just changes. 0 photon line goes slightly up. You can't get rid of the photon sidebands completely. They just change their shape. Okay, so what we use for this is a very simple setup. You have a green laser, CW, you have an AOM, and an acoustic modulator to turn the laser on and off in a nanosecond time scale, and you direct this through an objective onto a sample. The sample fluoresces, and in the red photons, you direct them back through a dichroic mirror, and you go to a photon counter that counts single photons, in our case, mostly tiny vacuum. There are also microwaves in the candidator here that we'll see later for right now. So here's is a picture of the setup. So the diamond is sitting here. And then the green light laser is coming from the bottom, and also the photons are going down. And the size of the crystal here is about 4 millimeters. This is the cover slip, which is about, I think it's about 1 inch. You see additional feature that we're going to use in a second. We have here gold here. We have microstrip line to send microwaves through to then act in the spin. Usually have a permanent magnet to apply some magnetic field that we're going to use to split the energy levels of the emissions. Okay, so where are those NV centers? And usually if you buy these crystals and you put them under a microscope, you get an image like this. So you already see the black parts is no fluorescence, and you see all these bright spots, and most of them correspond to single NV centers that we record in the CE optical microscope image. You can tell the single ones simply because they all have roughly the same intensity, and they are quite diluted. So also the spot size here is diffraction limited. The photons originate from a single one. You can do other things. Very often we shape the surface to do photonic structuring or make tips or scanning. And this is just now an array of pillars, which some of them have NV centers at the end, and then you can take the image you see. Enhanced fluorescence, if there's, here there will be probably 1, there will be 2 or 3. So these pillars are made to have a few NV centers at the end. People have also looked at NV centers in these nanocrystals, which can be ingested or put into cells, ingested by worms, and just be used as fluorescent labels. So we mostly use these 2 types. You can do more nanostructures. We also make cantilevers out of diamonds. Some other structures to do scanning. So now let me get back to the energy level diagram. We looked at the electronic levels. So now let's focus on the spin energy levels. So you have the spin 1. So spin 1 has 3 levels, 0, plus, minus 1. And naively you would think they're all, if you apply a magnetic field, they will shift. But it turns out if you have a spin 1, very often there's a so-called crystal field effect. So you could imagine you have 2 spins and you confine them in the same space. And because of dipolar coupling, there's now one preferred orientations. And it turns out the lowest energy state is if the spins, in this case, if you think of 2 spin 1 half or in opposite direction, and then it's a higher energy if they're pointing in the same direction. So this is just intuitively the reason why you have not really general levels. So the ms equals 0 has the lower energy, and then there's a degenerate plus minus 1. The difference here is so-called zero field splitting is about 2.8 gigahertz. So if you apply magnetic field, there's a Zeeman effect, so the plus 1 line will go up, the minus 1 line will go down, and the 0 line will now couple. So you now get 3 lines, 3 levels, and the splitting here is 2 times gamma, our coupling factor, which in this case is the general magnetic ratio given by the free electron G factor. So this number is a theoretical value here for an electron G factor equal to 2. And what we're now going to exploit is that as we apply magnetic fields, these lines shift. And we know exactly, if it shifts by a certain amount of frequency, 2.8 megahertz, how many Gauss this is. So we're going to do spectroscopy, find out what the energy level splitting is between 0 and minus 1, or 0 and plus 1, and from that we can infer what the local magnetic field is. In most cases, we focus on just the qubit. We don't use all 3 levels. Sometimes it's advantageous to use the 3 levels. But in most cases, we just use a subset. Yeah?
Do you see any variation in the coupling factor for ND to ND?
Okay, so good question. Does this vary? I mean, the next question will be, does the G factor of the electron in these systems vary? And for the ND center, basically no. So it's just the free electron G factor. If you go to other materials, the G factor can be different because of, let's say, spin orbital coupling. But in this case, everything is very high. There's basically no spin orbital coupling in ground state. So to a very good approximation, you just take the free electron G factor for given and it doesn't vary. Yeah.
Can you say again where the dipolar interaction comes from?
Here. Okay. The dipolar interaction was kind of a reasoning why you get at 0 magnetic field the splitting between ms plus minus 1 and ms 0.
But it's interaction between the electron spin and what?
Yeah. So it's if you have a spin 1 or higher system.
Oh, it's spin 1 system.
It's spin
There
1.
are 2 electrons.
Yeah, it's 2 unpaired electrons that point the same way. And when you have this, then very often you have this so-called zero field splitting. If you have a reduced symmetry of the location where the spins are. Okay. So how can we probe this? And what it turns out is that if you, for some way, are able to prepare your spin in the 0 state and now do a fluorescent detection, it turns out that you have a higher photon flux, a higher intensity, than if you, for some reason, are able to prepare your spin in the -1 state and do the same readout. So basically, we go back to our picture from here, we sit on one of those defects, and we simply analyze what is the intensity. So this effect that you're starting out of 0, lower intensity, a higher intensity, you start out ±1, lower intensity is not permanent, it's a temporary effect. And this can be resolved if you do a time-resolved experiment. So turn your laser off, and then you turn the laser on, and in a time-resolved way, you map what the intensity is. So this is an experimental trace here. It's averaged over many cycles. So no laser means we count no photons. As soon as we turn the laser on, there's a shoot up in red photons counted. And you see if you start out of ms equals 0, we have a higher intensity than if you start out of ms equal ±1. So the reason is, if you go back to the energy level diagram, we start out here. If you start out of 0, we mostly go up here and we cycle on this transition. If you start out of ±1, we do the same, but with a quite high probability, we actually go over to this third shelving state here. And this is quite long-lived, so if we do this detour, we spend a lot of time over here, there's no photons emitted, and on average the intensity is lower. There's a second effect. If you now go down from here to the ground state, you're always going to go down to ms equals 0. So it's an optical pumping effect. Whenever you do this detour, you go down to 0. Meaning if you shine light for a very long time, you're always in the end going to make a detour and not end up in 0. So this gives us the optical pumping effect, and it actually allows us to initialize the spin. So we use the same laser light to both initialize and read out the spin. So you see all this happening here. We turn on the light. Here in the red one here, we get a dip in fluorescence, meaning because we go over with some probability this shelving state. And if you wait long enough, the blue and the red curve, they align. Meaning now we have roughly the same. We pump back to 0, and we have initialized the spin. So what can we do here? How can we find out what our spin state is? We just integrate. We look at the initial part, the first few hundred nanoseconds. We integrate counts, and this is what we compare. We have a higher integrated count in this area than we are in the 0 state. We get a lower integrated count in the ±1 state. And once we turn the laser off, we end up in 0, so we have to re-initialize. To give you two numbers relating to yesterday, the initialization efficiency is quite high, so at this endpoint here, you're with a probability of higher than, let's say, 90% in the 0 state. So we're pretty good at initializing the epicenter. The readout efficiency is extremely poor. And one reason is because this contrast here is actually quite small. It's at most about 30%. And the other one is we're very bad at collecting photons. So during this period here, there may be a few photons emitted, let's say 5 or 10. We usually collect about 1% or even less of those photons. So if you combine everything, this moderate contrast and a few photons, we're actually able to extract from diamond and get them to the counter. We get an efficiency of, let's say, 1%, or our C factor is extremely small. So in order to record this trace and make a statement, whether up or down, we have to repeat for maybe 100,000, maybe 1 million times the same experiment. So we have to look at things that are repeatable. We cannot probe something which changes too rapidly. So there's ways to make this readout much more efficient, and this is by going to low temperature, and I'm just putting this as a side note. At low temperature, you can actually excite resonantly at the 0 phonon line. So if we now look very precisely in optical spectrum at the 0 phonon line, you see there's actually several lines. And all those lines correspond to resolved spin energy levels. So now you can go on to one of those very narrow lines, and one of them, this one here, for example, corresponds to a transition out of ms equals 0, and this one on ms equals ±1. So if you now just have a very narrow band laser focused on this line here, you can do counting statistics, and this is taken from one of Ronald Hanson's experiments in Delft, where he did spell test. So then you can very easily tell if you have photons, blue curve, then you're in ms equals 0. If you have no photons, then you're not in ms equals 0, ms equals ±1. Yeah.
Can you tell me about the 0 phonon lines?
Okay, the 0 phonon line is if you excite, let's say, from ms equals 0 here directly to ms equals 0 in the excited state, and so the energy of the photon you put in is exactly the energy difference between ms, this level here and that level here. Meaning, so the energy you put in is 100% going in your electronic excitation. In most cases, if your laser energy is higher, so waveform is lower, you can still excite the system. But now the energy is higher, so your electron is technically in a higher energy level, and it has to give away the excess energy to phonons. So, meaning, in this case, phonons are created. The 0 phonon line means just if you excite the electron, there are no phonons created. All the photon energy put in goes 100%.
This is why also the emission spectrum is really broadband, because it has several nanometers.
Yeah, so this is what you see here. So you have here the onset. At this point, if your laser energy, so I'm looking at the absorption here. If the laser energy is too low, you're basically not exciting your system at all. Once you come to the zero phonon line, the energy of the laser is just sufficient to go from the ground state into the excited state. If now the wavelengths get smaller, laser energy is higher, the MV center still absorbs the photons, but now the energy is too high, it gives away the excess energy into phonons, and this is where you have this broad absorption line, and well, it rapidly accumulates at the upper energy level. So meaning it's just if your photon energy is too high, you can still absorb it, and actually absorption is even higher at this lower wavelength.
But if the energy structure is independent of the band structure, then why does that happen?
Okay, I don't know whether I could explain here. So what's shown here is the spin energy levels and the electronic energy levels. What's not shown is vibrational energy levels. So the vibrational energy levels make that those levels are not discrete here, but they're actually smeared out. So there's a whole range of levels here with that belong to different phonons. And I'm only showing you the lowest energy one. No phonons created. But there is a whole band here, and you actually excite from this lowest level here to somewhere in this band of electronically excited states, which corresponds to the phonons. Let's talk later.
Okay.
Yeah.
What's the line width of the lifetime of the zero phonon line? And what is it?
Okay, good question. I don't know. Usually those are short-lived, and they're picoseconds in this case. But, so I guess you could go through an analysis, so a mode analysis of the photons. So what really happens if you excite it, the MV center, it has some electronic wave function, which is in this case mostly vacancy. If you go to the electronically excited state, the wave function changes. So this change in wave function will push out the carbons around here. So in some sense, you create a wave or some excitation in the carbon lattice, which are your phonons. So it comes from a spatial change of the wave function going from here to here.
Oh, but in the case of the zero phonon line, there are no phonons. Right?
Yeah, there are no phonons created in that case. But it's a rare event. In most cases, there are phonons created because the wave function changes.
Sure.
Yeah, it's in 1% usually.
So very naively, as far as the readout is concerned, so the way you've drawn the level diagram, it seems like the state with S, ms equals 0 is S decays to ms equals 0 in G. So is it not possible to just probe on that too? And on the side transition to, so that you don't excite ms equals 1. So if you're in 0, you just get fluorescence, otherwise you don't get fluorescence.
So if you're at room temperature, there are these phonon side bands, then those lines are not resolved in the optical spectrum. It's just a broad line. So you can, of course, take a laser which excites exactly from the ms equals 0, but you cannot prevent that you also would excite ms equals plus minus 1.
Okay.
If you go to low temperatures, lines become very narrow. And this was this zoom in I showed on the last slide, which was this one here. So if you're at low temperature and you really zoom in, you now actually start to be able to resolve the optical lines. But you can only do this below 10 Kelvin. And then you can do exactly what you say. You set the laser to exactly the transition from the ms equals 0, which in this case is this EX line here and more. But if you excite this one, it has come from ms equals 0. And this gives you now a much better contrast. In this case, you can basically be sure if you collect a photon, you have excited that line, it was in ms equals 0. So one photon in that case is enough to tell, okay, I was in ms equals 0, I'm not in ms equals plus minus 1. So there the contrast is, so to say, 100%. If you use this room temperature, non-resonant, green-red excitation, the contrast is only about 30%.
So it's not like an atomic system where the polarization of the light is going to determine which kind of line level you're excited to. It's like bipolarized to signal. It's not like that here.
Okay, so in this case, there's actually polarization associated with the lines. There are actually two optical dipoles in the excited state, so it becomes a bit more messy. So at low temperature, in principle, you can, from the polarization of the light, to some extent control which line you're exciting. At room temperature, this is much less because there is still a slight dependence on polarization, but it's very small, and you can't really exploit it. You can use it to maximize your efficiency, but it's not something that gives you the clear mark. Okay, so now let me show you some experiments now trying to resolve these spin states. So we've seen now we are able to initialize or prepare the system in n equals 0, and we are able to read out or determine whether we are in 0 or 1. So we have the two basic tools. We can initialize and we can read out. So the third one, what we want to be able to manipulate. So we want to be able to controllably move the qubit from here to here. You do this by applying resonant photons, so 2.8 gigahertz photons, which are microwave photons. And this is why we have this microwave strip line. And the simplest experiment you can do, you can just shine green light constantly, so you're constantly repumping it to 0, and on top of it, apply a microwave field where you dial through the frequency. And if this frequency matches these levels, you're going to excite partially into ms equal -1 or ms equal +1, and you get a non-equilibrium situation, and your intensity is going to drop because you now have a probability during one of the higher states. So this is how the experiment looks like. So you record intensity, but you slowly change the microwave frequency, and as you get to the resonance, intensity goes down. So this is simply a single electron spin resonance curve that shows you the level splitting is 2.87 gigahertz in this case, at 0 field. So the next thing, you can apply a field, 2.8 millitesla, you see the line split. You can go higher, and you can go even higher. And you see that the difference here is now given by our proportionality factor, is gamma, 2 times gamma times the magnetic field. There's a detail to it. We have to apply this field along the axis of the NV center. It's another consequence of having spin 1. So whenever we report these field numbers, it's the projection of the magnetic field on the axis, the NV axis. So when you see magnetic measurements with NV centers, it's always a vectorial measurement. It's the measurement of the component of the magnetic field along the axis of the NV center. Okay, so these are the very basics of how the NV center as a qubit works. And this is the key slide here to understand how we can measure magnetic field. We look at the change in the spin resonance using optical detection. So let me now show you 3 examples of the protocols we've seen yesterday. So we've seen just basic spectroscopy, then the Ramsey measurement, and this redoxometry. And you can do all of them quite easily with the NV center. So the first one you've already seen, that was spectroscopy, but you can now quantify this and do it better. So we now zoom in on one of the 2 lines, it's the 0 to -1 line. And we recorded many points, and in order to know what the magnetic field is, we fit a line, we determine the center value, and then we just convert from units of frequency to magnetic field using this well-defined gamma factor. So in this case, the magnetic field derived from this 2.64 gigahertz was 8.23 millitesla. We can just slightly change the field, and we change it here by about 100 microtesla. Line shifts, and we can tell how the shift was. So this is a very basic experiment, how we just look at locally how this line changes. You can do this also with Ramsey interferometry, and we use our basic tools that we've seen yesterday. We initialize the system. We do this by doing laser pulse, optical pumping. We just apply the pulse. We don't care about how many photons we're collecting. We're just sure at the end we're in 0. Then we add on top of it some microwaves. So we apply a microwave by half pulse to rotate the Bloch vector into the XY plane, and then we let it precess for a certain amount of time. After a certain time, we flip it back to 0 or to up or down, 0 or 1, and we do a readout. So in this case, we count the photons. We look at the photons in the first few nanoseconds. We can repeat this for a whole series of tau values, and then we can build up this oscillation here. We can fit the oscillation, and on the oscillation frequency, we get, in this case, the field, 4.533 millitesla. We can repeat this again for a slightly different field, 10 microtesla apart, and we see it's quite a different oscillation. So the sensitivity in this case is probably better than microtesla. So this was our second scheme. Yeah.
How does this microwave rotation works?
Say again.
You apply microwaves to make this pi-half rotation.
Yes.
How does it work?
We just turn the microwaves on resonantly for a certain amount of time, long enough to make a Rabi oscillation by an angle of 90 degrees. So it's like the Rabi oscillations you've just seen in the previous talk. But we make it just as long that we do exactly 90 degree rotation. And then the same set. Okay, there is a third example for this relaxometry. So here is a relaxation curve of this epicenter. Again, we prepare at 0, we do nothing with microwaves. We wait for some time tau, and then we read out are we still in 0 or in 1. And this is for a nanodiamond here, which have very short T1s because they have many impurities. So the T1 time, the decay time is only over 40 microseconds. So what we now can do to change this, we can put something magnetic around it, so magnetic environment which fluctuates very fast at the resonance frequency of our epicenter, so around 3 gigahertz. And then these fluctuations enhance the spectral density, and we should get a faster decay. And what we used here is a specific salt. It's a gadolinium salt that's used in MRI imaging as a contrast agent. And it has the property that it very rapidly fluctuates. It has a very high electron spin on the order of a 10 gigahertz correlation time. So it creates very strong noise up to about 10 gigahertz. So if we now have this nanodiamond, if we put the salt around it, then you see an extremely drastic change in this case of the relaxation. You see the relaxation time drops by a factor of 10, so this is a lot, usually it's less. And we can immediately tell, well, there is some fluctuations going on, we could even quantify it. This is very interesting for, again, bio applications. People are trying to put nanodiamonds into cells, and if we have now a magnetic ion, let's say manganese, in principle you should be able to locally probe the concentration of the magnetic ions. So one thing people are trying to do is to have MV centers and nanodiamonds in cells, measure these relaxation times, and from that infer the concentration of the magnetic ions. Yeah.
But how do you put pulse in it? How do you put the vibrator pulse?
Okay, talking about paleo 2 pulse?
Yeah.
Not in this case, in this experiment before. So here there is no pulses at all. You just have a laser.
How would you excite it in any case, to make any experiment once you put it inside a file sample?
Okay, so if you were to carry out this, well, the scheme up here stays the same. But if you would do it in a biological sample, you pulse the laser, and then you wait for some time, and you pulse the laser again, and during the second time, you count how many photons you get in the emission.
So you can do it for live samples?
People have done it for live samples. So if you go to biology, things get all different. So people have figured out quite well how to get objects like nanodiamonds into cells by modifying the surface, even directly in cells to certain areas, let's say the cell wall or to the boundary between the nucleus and the nuclear membrane, or let's say to mitochondria. So people know how to do that. And then the experiment itself, the analysis, so fluorescence microscopy is a very common tool in biology. So what we add on top here is that we actually prepare a spin using the fluorescence, and we're looking at intensity changes as a function. So I don't think this has been done in live cells. There are other experiments. You can also measure temperature, which I'm not going to show. I'm running out of time here. But temperature modifies this value here. This zero field splitting is 2.87 gigahertz. They shift with temperature. People have exploited this to actually trying to locally probe temperature in cells. And this can be very interesting because if you have these mitochondria, if they get very active, they produce energy and you would expect that temperature. Okay, yeah, see, I'm running out of time, but I wanted to, these are 3 examples I wanted to show you on a last slide. the tool that we actually use in the experiments to go through the whole theory. How do we carry out an experiment and we end up with a value? So here is now a more complex experiment, and it's actually an experimental data I'm going to show how we carry out on a larger scale these NV-centered experiments, going from this very basic scheme where you have a laser pulse, a time, and another laser pulse, to do a whole analysis for quantum sensing as an applied tool. So what we by now use in our lab is a time synchronized version of quantum sensing. So usually we have a clock oscillator that starts and triggers the experiment. You've seen we have two ways to operate our qubit. We have a laser to initialize it and trigger the readout, and we have microwave pulses. So we have a laser which is triggered by the clock, and we have microwaves which use an arbitrary waveform generator to synthesize the pulses. And once the clock says go, the experimenter says go, both of them run on the same clock, and they just play a certain series of laser pulses, a certain series of microwave pulses. So in the next step, we have to collect photons. We have the single photon counter, and these modules, they create a click whenever a photon arises, and the click can be counted by a digital counter and tell you at what time the photons arrive. So whenever we have a click, we record it and we note down the time. So we can, each photon that we collect, we can align it somewhere in the sequence. So what you see here now is not one series of clicks, but it's about 1 million repetitions. So we can build up a histogram and look relative to our sequence, when did the photons arrive. And you may recognize these two blue curves here, which are very similar to the curves you've seen in the time result experiment, where you see that the intensity is higher for ms equals 0, it's lower for ms equals plus minus 1. So this duration is roughly 1 microsecond. So now we have, in a synchronized version, we have a whole series of pulses, whole series of microwave pulses, and we have photons that we can now combine or attach to certain times in our experiment. So the next thing we do is we integrate the first portion of our photons here, where the information is contained. So the first few hundred nanoseconds have a higher or lower intensity, and you can see very clearly here, high intensity here, low intensity here. This is actually ms equals 0, here is ms equals plus minus 1. So we can integrate, so we have an integration or a gate that just tells us integrate this amount of photons over that time. So this gives us a number of photons. So you get some photon counts associated with each integration window, and you see already here, if we have divided up the experiment, we actually first, before we perform a read experiment, we record two references. We just look at what is the photon count in ms equals 0, and what's the photon count in ms equals 1 or minus 1. This one is easy, we just initialize by laser pulse. The second one is very similar. We initialize by laser pulse, and with the microwaves, we apply a pi pulse, so we invert this bit system. And then here, this is the actual experiment. In this case, it was a so-called dynamical decoupling experiment, where we were trying to preserve the coherence for a very long time. And we get for each readout here a photon count, and what we then do in the next step is that we analyze, we use the reference to, from these photon counts, calculate probability values, with which probability was one of those outcomes in 0 or in 1. And we're not going to get 0 or 1, because we have now already repeated the experiment many times. We're going to get a fractional value between 0 and 1, which is already the probability that we were trying to get from the Bayesian estimation. And then the final thing we're going to do, we plug these probability values into some algorithm that in the end gives us the final output parameter, like a field value or a noise intensity. So I'm showing this because this is how far advanced the experiments have gone. And you've seen the very basic ones, but by now we run sequences, so the clock time is usually 1 nanosecond. The excerpt you see here is in order of 100 microseconds, but you have experiments that go up to 1 second and have here between 10,000 and 100,000 pulses. So the cool thing is here you can, in a time-tagged fashion, play a whole series of pulses, and you can extract photons and construct from the photon counts the parameter that you want. So in some sense, this is the vision of applied quantum sensing. You have all these manipulations plugged in that you get from theory. You get counts, then you do an analysis, which can be very elaborate using parameter estimation methods, and the output is, let's say, a field band. Okay, I'm running out of time, so I guess I'm going to stop here, and I may show you some of the additional applications on Friday. So one would be scanning with MV centers, and then the biosensing code. I'm not going to get to.
Lively discussions. Questions?
Yeah.
I have a question. I love diamonds. When you mentioned that they create these vacuums inside the diamonds that you get from either the nitrogen or the vacancies that they get created. By any chance, do you think they will create crack in the real diamonds or the ones that you use?
Okay. Yeah, so there's a lot of things that kind of go wrong with diamond. Okay, there's many things. One can say it's the hardest material, so it's very hard to scratch it. It's chemically very inert, so it's very hard to destroy down. It can be cleaved. So the diamonds we use are single crystal. They usually have a 1-0-0 surface orientation. If you hit it the right way, it will cleave along the 1-1-1 axis and expose a different type of surface. So it can get cracks. You have to create vacancies, and this is actually can be quite some problem. So we create vacancies because we need them for MV centers. If we create too many vacancies, there are more extended defects forming. Usually it's not really cracks, but there's, for example, double vacancies forming. So two vacancies attached together. They're bad for us. The single vacancies are not that bad. They usually diffuse quite well, so you can anneal them out. The divacancies, they are not annealing out that well. You have to heat the diamond much higher, which then bears other problems. Also, they're usually electron acceptors. We've seen we have an ND minus, so we want an extra electron from somewhere. Usually it's from nitrogen, which is a donor. So divacancies, they actually are scavenging the electrons, and they are detrimental to the charge stability of ND centers. And there's many more defects. So diamond has been studied for 50 years, but there's still defects being discovered. People don't really know what's going on. So I think it's going to continue to be a material, although we know the MV center quite well, we don't by far not know it.
Right. Thank you.
Yeah.
Do you care about the density of these NV centers in diamond or their proximity to one another?
Okay, do we care about the density? Yes, we do. So it depends on the experiment again. We work with single NV centers, so we usually try to keep the density low. If they're too high, it means not only that we have many NV centers, but also a lot of other defects. Usually the ratio of NV centers to nitrogen, for example, is, so nitrogen is 10 times higher or 100 times higher. They carry a spin, so they're a magnetic defect, so they may shorten our T1 or our T2. There are some applications, you see these pillars that we use for scanning, which I may get to talk on Friday. There we need one NV center in a very short tip, so we have to tune the density that we on average get 1 in the tip, which is higher than the density we usually like. People also use extended surfaces, so not use one NV center, but many. Usually not in this entanglement mode, but just to operate them in parallel. And then you want to make the density as high as possible, because now more sensors per area. If that density gets too high, your T2 times are going to drop and go down. So then there's an optimal. Should I make the number higher, or should I reduce the T2? So you can control the density. You try to work out low density first. Yeah.
Can you extend to longer T2 times in your nanopillars, since they're less nuclear spins around?
Okay, so can you extend T2? You can, but usually what's really affecting the NV center in terms of spins is really the local environment, the first few nanometers.
Okay.
So by nanostructuring, you're not going to get that. In fact, it makes it worse, because nanostructuring usually leaves a rough surface, which has a lot of surface defects, and usually that's actually bad. So you want to have an atomically flat surface. So you have to work in another way. You have very few NV centers, which usually means very few other defects. And many people work with isotopically purified carbon to reduce the extra carbon. Sometimes it's helpful, sometimes it doesn't. Yeah.
Can you comment a little bit on the mechanisms behind the readout errors that you get?
Okay, so I showed the readout is really bad. I mean, you don't get single shot readout. There are actually tricks to get single shot readout, like these low temperature methods. There are a few. So the main problem we have is that the photons that we collect, the number is very small. You see we have this window of a few hundred nanoseconds to collect photons before we repump in the zero state. So we get, let's say, there are 5 photons emitted before the repumping happens. Out of those 5 photons, we collect 0.1 or less. So it's very hard to get the photon out of diamond. It's a high refractive index material. Go through your optics and arrive at the detector. So the best hand we have is nanostructuring or shaping the diamond such that the extraction efficiency gets higher. And this is why we also use these pillars. There are photonic waveguides which direct the photon one way. There are other ways. You can use solid immersion lenses. People have to kind of parabolic mirror reflectors, so you can bring this number up by a factor of 10 or even 100. So this is the biggest hand. And then the other thing that hurts is this limited contrast. You've seen there is a photon intensity contrast between 0 and plus minus 1. It's not that big. It's maybe 30%. And this really also hurts you, this makes you need many photons to be able to tell the 2 states apart. And again, you have low temperature winds, because if you're able to address one line resonantly, you have essentially 100% contrast. So you need very much fewer photons to actually make a decision which state you use. Yeah?
In the first few slides, you introduced the entanglement between qubits.
Yeah.
In this case, can you entangle different resonators at different locations?
Okay. So in principle, you can. It's very hard. So how we've gone a bit that way. And the way you do it is you plant nitrogen N2. So you create this NV center sometimes by ion implantation. You shoot an N2 molecule such that 2 nitrogen atoms end up in diamond, but very close, and then you hope both of them form NV centers. There is another way which actually is more clever and which has been used, which takes advantage of that the NV centers in Q trig and not in qubit. So if you go back to the energy level, spin energy levels, here you can actually, you have 3 levels. In some sense you have 2 qubits. So you can create superpositions between those states here. And then actually you gain this factor of 2. And it turns out T2 is shorter, so this is where the compromise happens. So we can, with one NV centers, to some extent, play this game of using entanglement. And in this case, it's not really entanglement, we just call it a double quantum transition between those states. But you can exercise this to some extent. With several NV centers, it's pretty hard, because it's very hard to producibly generate them very close to each other. Yeah. So the very long one at the end. This one here.
For the microwave process, is a single one images to the power channel and the signal is the power.
Yeah, so this should be a symbol for any sequence, but in practice, yeah, this is an experiment where the shorter one here will be at pi half pulse and the thicker one is at pi pulse. So this is roughly the sequence that actually is behind. So this is experimental data here, and this I kind of just made up to illustrate, but it reflects what the experiment has been doing. So here, this will be pi half pulse, and the thick one will be a pi pulse.
My question is, what does the pi pulse do to
Okay, to the photons, to the spin.
Yeah, to the spin of the
Yeah. Okay, I'll get to talk about this on Friday.
Okay.
But so what a pi pulse inverts the spin.
Yeah.
So it either turns it from up to down, which is what the idea of this pi pulse here is, because you can prepare it in 0, turn it from up to down, and then in 1. This then allows you to generate this reference. In this case, we're in a coherent, in a Ramsey experiment, where during the Ramsey experiment we apply additional pulses, and those form spin echoes. So this will be a very basic spin echo here. You apply a pi half pulse to create a Ramsey precession. In the middle of your Ramsey sequence, you make a pi pulse, which rotates your spin over Z, so to say, in the blast sphere. And then it forms a spin echo at time times the second ITAMP pulse. So, well, I guess the basic answer here is it's used to make spin echoes. But I don't know whether you're familiar with spin echoes. It's a way to prevent decoherence or dephasing of qubits. But I want to talk more about this on Friday.
After the first half cycles, all the population is on the crater of the Block-sphere.
Yeah.
What happens after you apply the hypothesis? If it is a crater plane, if it's here, then it rotates to the other side of it.
Yeah, roughly correct. So it stays on the equator, but just it points in a different direction. You rotate it to another position on the equator, let's say opposite direction, depending on the axis of rotation. But it means you just always stay on the equator.
There's like the best animation ever created on Wikipedia for spin echoes. So yeah,
Okay, I should look that up because
everyone should look at that.
someone else gave me also the best.
Oh,
Python. Maybe I should look that up for Friday.
it's probably the same.
Python one. Some people in Oxford, but okay, I'll try to dig that.
I can show you.
Yeah.
So why don't we take the last question?
Yeah.
Another question?
Yeah, maybe you want, I thought, Friday, right? You use this background of the counting sequence, you really sensing, because it seems like kind of like
Yeah, okay, so maybe this is supposed to be a teaser for Friday, where I'm going to show the dynamic decoupling. But yes, we do. It's one of the most elementary building blocks if you want to sense time-dependent fields, not static fields. So the Ramsey measures just a DC magnetic field or a shape of DC field. Using these dynamical decoupling or echo sequences, you can actually make it sensitive to AC fields. And this is what we're going to explore it right now.
Okay, then, join me in thanking